This problem is about equilibrium of rigid bodies, in this case, a three-dimensional system. In this question, we have two gears, B and C, attached to an axle AD, which is supported by bearings A and D. Radius of gears B and C are given 10 inches and 15 inches respectively. The moment reaction at bearings A and D are assumed to be negligible, and they only resist force reactions. Bearing D does not exert any axial thrust either. A force F parallel to the z-axis applied to the top of gear C as shown. We are to determine the vertical force P applied to gear B and the force reaction at bearings A and D. Obviously, we need to draw free body diagram of axle AD as follows. Axle A, B, C, D is shown here. Dimensions are given. AB equal to 30 inches, BC 70 inches, and CD equal to 50 inches. We can keep the forces on the top of gear C and on the side of gear B, or replace them with the force and couple at center of the axle AD. I'm going to choose the second option. Therefore, we are going to have a force F equal to 900 pounds applied to the center of the shaft. At the same time, force F creates a moment about x-axis MC. The value of MC is equal to the force 900 pounds times the radius of the gear, 15 inches. And since it is clockwise, we should get a negative sign with the magnitude of 13,500 pound inch of M about the x-axis. At the same time, we have a force P, which is unknown, and also a moment about x-axis at B equal to MB. At A, we have three-force reaction, AX, AY, and AZ. At D, we have dy, dz, and no dx because it has no axial thrust. As we can see, there seems to be 7 unknowns: ax, ay, az, p, mb, dy, dz. However, mb is equal to p, force P, times 10 inches, which is the radius of gear B, and the magnitude of this moment is 10 p pound inch again, and this is the moment about x-axis as well. As a result, we have 6 unknown left, and we have, of course, 6 equations of equilibrium. The first equation of equilibrium is summation of the forces about x-axis equal to 0, and we only have ax, therefore ax must be equal to 0. Summation of forces about y-axis are ay minus p unknown plus dy equal to 0. Summation of the forces parallel to the z-axis equal to az minus 900 pounds plus dz equal to 0. So we have used all 3 equations of equilibrium for forces. Next, we need to write summation of the moment about a point equal to 0, or instead use summation of moment about x and y and z axis to be equal to 0. First, let's use the summation of the moment about x to be equal to 0. We note the three components of the reaction force at bearing A, AX, AY, and AZ do not have any moment about x-axis because they intersect the line. At point B, we have a counterclockwise moment MB, unknown, but force P does not have any moment about x-axis either. At point C, we have a clockwise moment MC with a magnitude of 13,500 pound-inch, and the 900 pound does not have moment about x-axis also. Similarly, dy and dz do not have any moment about x-axis, so sum of these two moments must be equal to 0. However, MB was equal to 10p, so our equation becomes 10p minus 13,500 pound-inch equal to 0. And we can calculate the value of P to be equal to 13,500 pound-inch divided by 10 inches equal to 1,350 pounds. Next, we need to write the summation of the moment about the y-axis to be equal to 0. Looking at the free body diagram, none of the forces at A have any moment about the y-axis. MB is a moment about x-axis. P doesn't have any moment about y-axis. However, force 900 creates a moment about y-axis. Therefore, we have 900 pounds multiplied by distance from C to A, which is 100 inches. If we are using the right-hand rule, putting our finger along the force F, turning it around y-axis, we see our thumb is upward, therefore this moment is positive. dy does not have any moment about y-axis because it is parallel to it. However, dz has a moment similar to the 900 pound, but dz distance is 150 inches and it creates a moment negatively about the y-axis. Therefore, we have to assign a negative to it. From this equation, we find dz equal to 600 pounds. And since it is positive, the direction of our reaction is correct. Looking back at equation 3, we can see that AZ is equal to 900 minus dz, or equal to 900 pound minus 600 pound equal to 300 pound. The last equation of equilibrium is the moment about the zx. Again, all forces at A do not have any moment about zx. P has a moment about the z-axis negatively, therefore we have minus P, and the distance is 30 inches. Also, dy has a moment about z-axis, dy, and the distance from the z-axis is 150 inches. And this one creates a moment positive or counterclockwise about the z-axis. Setting it equal to 0, we'll see that dy become equal to P. Value of the P was 1,350 times 30 inches divided by 150 inches equal to 270 pounds. Finally, from second equation of equilibrium, we can see that AY is equal to P minus dy, or equal to 1,350 minus 270 equal to 1,080 pounds. All the question being answered.